Chapter 31: Atomic Physics. Here is the overview of Chapter 31. We will first talk about early models of the atom and how it was initially understood. We will then talk about the spectrum of atomic hydrogen and how that led to developments in a better understanding of the atom. We'll then move on to Bohr's model of the hydrogen atom, talk about de Broglie waves and how they relate to Bohr's model. Then we will discuss the quantum mechanical hydrogen atom, talk about how electrons are filled in multi-electron atoms and how that relates to the periodic table. And the final thing we'll talk about is atomic radiation. The electron was discovered in 1897, and even back then it was observed to have a much smaller size compared to the size of the atom. What was proposed for the atomic structure was something that was called the Plum-Pudding model as a result, and this model hypothesizes that the positive charge in an atom exists in a cloud and the negative charge is embedded in this cloud as tiny dots. After the hypothesis of the Plum-Pudding model, experiments were done to try and verify it. What was done was alpha particles, which are helium nuclei, and we'll talk about these in detail in the next chapter, were fired in a beam onto gold foil. What was found was pretty unexpected. It was found that many of these alpha particles had large angle scatters. A small angle scatter corresponds to an alpha particle not being diverted when it passes through the foil. A large angle scatter corresponds to a big diversion in the direction. Now, this is something that can only happen if we have a positive charge that was concentrated in a very tiny volume in the gold foil itself, and this was a rather different idea to the Plum-Pudding model, where in the Plum-Pudding model the positive charge was spread out over a much larger volume. These observations, which we described on the previous slide, led to the solar system model of the atom, and in this model we have electrons which orbit a small positively charged nucleus, much in the same way as planets orbit the Sun in our own solar system. Now, if we look at light emitted by a low pressure hydrogen gas which is subjected to a large electric field, and we pass this light through a diffraction grating, and the diffraction grating will separate the light into various wavelengths, we find something called a line spectrum, and that is that the light only consists of a small number of wavelengths. In this case we have one wavelength corresponding to purple light, two corresponding to blue, one corresponding to yellow, and another corresponding to red. It turns out that each atom has its own particular set of lines that it will emit when placed in the same situation, and if we then pass white light through a particular atom or a gas of atoms, it turns out that these atoms will absorb exactly the same frequencies as they emit in the experiment on the previous slide. the absorption is shown by the bottom picture. It was found that the wavelengths in the visible spectrum that are seen in these lines can be described by a relatively simple formula where 1 over the wavelength equals a constant called the Rydberg constant times 1 over 2 squared minus 1 over n squared, where n corresponds to a particular line. This is referred to as the Balmer series of spectral lines, and this Rydberg constant R is equal to 1.097 times 10 to the 7 inverse meters. Now, these observations interested a scientist called Niels Bohr, and he proposed a model to try and explain them. The model has 3 assumptions. The first assumption is that the electron in a hydrogen atom moves in a circular orbit around the nucleus. The second assumption is only certain orbits are allowed, and these are dictated by their angular momentum, where their angular momentum has to be equal to n times h, Planck's constant, divided by 2 pi. The third assumption was that when radiation is emitted, this corresponds to an electron changing from one orbit to another, where the frequency can be determined by the changing energy, and the change in energy will equal to hf. In order for an electron to move in a circle of radius r at speed v, the electrostatic force must provide the required centripetal force to have this circular orbit. This means that mv squared, which is the centripetal force, has to equal k e squared over r, which is the electrostatic force. The same principle applies for gravitational orbits, where the gravitational force has to equal the centripetal force in order to have a circular orbit. When we add in our angular momentum constraint, this gives us a velocity which depends on n, which is an integer, and this velocity is equal to nh, Planck's constant, divided by 2 pi m, the mass of the electron, Rn, the radius of the orbit. Solving the previous equations gives us an equation for the radii in terms of n, which again can be any number that is an integer, and the radius Rn is equal to h squared divided by 4 pi squared mke squared times n squared. Now, the quantity in parentheses is actually the radius of the smallest orbit, which corresponds to n equals 1, and that is equal to 5.29 by 10 to the minus 11 meters. Now, the Bohr model can not only be applied to the hydrogen atom, but it can be applied to any single electron atom by taking into account the different Coulomb force. And the different Coulomb force will come about from an increase in the number of protons for the nucleus. A hydrogen atom has 1 proton. This can be generalized if Z is equal to the number of protons as Rn is equal to h squared over 4 pi squared mkz, the number of protons, times E squared, close parenthesis, times n squared, where n can be 1, 2, 3, 4, etc. Now, the total mechanical energy, E, is the sum of the kinetic energy of an electron in an orbit and the potential energy from the electrostatic force. If you calculate this, you can show that it's equal to minus 13.6 electron volts times Z squared divided by n squared, where Z is the number of protons and n is an integer. We refer to it as a quantum number sometimes, and that can obviously be 1, 2, 3, 4, 5, etc. The lowest energy corresponds to the ground state, and that corresponds to n equals 1, and for most atoms the electron at room temperature lives in the ground state. Now, if we assume that the radiation emitted from excited atoms corresponds to a change in the electron energy levels, we can determine exactly what the wavelength should be from the Bohr model itself. 1 over the wavelength is equal to 2 pi squared times m k squared e to the 4 divided by h to the 3 times c times 1 over nf squared, where n is the final quantum number, minus 1 over ni squared, where ni is the initial quantum number. It turns out the constant in parentheses, which has the mass, the Coulomb constant, the charge of the electron, Planck's constant, and the speed of light, exactly equals the Rydberg constant that we discussed for the Balmer series. This essentially meant that the Bohr model was able to reproduce the equations that describe the Balmer series, which in a sense validates the three main assumptions of the Bohr model that we discussed on slide 9. Now, de Broglie came along and he proposed another way to look at electrons in orbit of a nucleus. What he proposed was that the only allowed orbits would be integer numbers of the de Broglie wavelength of the electron. For example, if the orbit that corresponds to n equals 7 were to exist, then there would have to be 7 of the electron wavelengths within that orbit. For the orbit n equals 8, there would be 8 of those orbits. Orbits that didn't correspond to this condition were said to experience destructive interference, and by that he just meant that they can't exist. So, using the previous hypothesis, one can calculate what the momentum of the electron can be. The momentum is equal to mv, which is also equal to h over lambda from the previous chapter, and if lambda is subject to the orbital restrictions that we discussed in the previous slide, then that has to be the circumference divided by n, where the circumference is 2 pi r. This gives us a momentum that's equal to nh divided by 2 pi r, where n has to be an integer, and one can then show that the angular momentum, which is r times mv, will equal nh divided by 2 pi, and this is exactly one of Bohr's assumptions. After the Bohr model, a more sophisticated and, it turns out, more correct model of the hydrogen atom was devised, and this is the quantum mechanical model of the hydrogen atom. It has 4 quantum numbers rather than just the 1. It has the principal quantum number, which is denoted as n, and this essentially tells us the energy of the electron. The energy will be equal to minus 13.6 electron volts divided by n squared, and this energy is the total energy, i.e. the kinetic energy added to the potential energy. The second quantum number, L, is associated with the orbital angular momentum of the electron that orbits the atom, and the orbital angular momentum L is given by the square root of L times L plus 1 times by Planck's constant h divided by 2 pi, and L can take any value from 0 to 1 all the way to n minus 1, where n is the principal quantum number. The third quantum number is the magnetic quantum number, and this is relevant when a magnetic field surrounds an atom. This number, ml, can take any value from minus L up until L, but that value has to be an integer. There is a z component of the angular orbital momentum, which is associated with this number, and that is equal to ml times h divided by 2 pi. The fourth quantum number is the electron spin number. This relates to an intrinsic property of the electron, its intrinsic angular momentum, and this can only take 2 values, which is minus a half or half, and it's denoted with ms. Now, a state is defined as a particular assignment of these 4 quantum numbers, given the restrictions that we just discussed. One example of a state refers to n equals 1 and L equals 0. We can have an ml as 0 and an ms as a half. We can also have the same nl and ml numbers and have an ms state of minus a half. Then, if n equals 2, we can have a situation where we have L is 0 or L is 1, and when L is 0, ml can only be 0, and we can have 2 states, which corresponds to ms of a half or ms of minus a half. When n equals 2 and L equals 1, this allows us to have a variety of ml states which go from minus 1 to 1, and for each ml we have 2 ms states, half and minus a half. Life gets much more complicated when there are multiple electrons in an atom, and there are no simple formulas for the energy levels and how they relate to n. However, we can still characterize multi-electron atoms with the same quantum numbers. So an electron can have a state where n equals 1 and L equals 0 and ML is 0 and MS is a half, etc. On the right, we have a diagram of the energy of various states. The shell refers to the n number, so n equals 1 corresponds to the k shell, n equals 2 the L shell, etc. And the subshell can have different values, and that corresponds to the different L's that are allowed. And the L equals 0 subshell we refer to as S, L equals 1 P, L equals 2 D, etc. The Pauli exclusion principle states that only one electron can exist in a particular quantum state. By that, we mean that one electron at a time can only have a particular set of quantum numbers N, L, ML, and MS. Once that state is occupied, i.e. an electron takes those numbers, no other electron can have the same numbers. Therefore, if we add electrons to an atom, they must go into higher energy states, which correspond to states with larger quantum numbers. This means that each energy level can accommodate a certain number of electrons, which depends on n. For instance, for the n equals 1 shell, there is only one possible value of L, which is equal to 0, and there is also only one possible value of ML, which is equal to 0, but there are two values of MS, minus a half and a half. That means the n equals 1 shell can accommodate 2 electrons because there are 2 different quantum states. The same argument can then be applied for n equals 2, n equals 3, etc., where the number of states grows quite a bit when you increase the n number. The electron arrangements are given here for the first 8 elements of the periodic table. So what we can see for hydrogen is the electron will occupy the n equals 1 state, and it will have an L of 0, an ML of 0, and either an MS of minus a half or an MS of plus a half. For helium, we have 2 electrons, and each of these electrons will occupy the n equals 1 state with L equals 0 and ML equals 0. One of the electrons will have an MS of a half, and the other electron will have an MS of a minus half. We can then extend the same arguments for lithium and so on and so forth, and the extra electrons they have will essentially occupy states with larger quantum numbers. We have a shorthand notation which is devised to describe the configuration of electrons in a particular atom. The diagram before shows how the various states relate to the energy levels. The shorthand notation example we have here is 3p6. The 3 is the principal quantum number, the p is the angular momentum quantum number, which corresponds to L equals 1, and the 6 is the number of electrons that can exist with an n equals 3 and a L equals 1. That number is determined by the possible ML states and MS states. For the case of L equals 1, that number is 6. Once every occupied level is described in this way, we have a complete description of the electron configuration of the atom with respect to these quantum states. For hydrogen, we have a configuration of 1s1. The 1 at the end corresponds to the single electron that's occupied in the subshell 1s. The helium atom has 1s2, and the 2 corresponds to the 2 electrons that occupy the n equals 1 and L equals 0 state. For lithium, we have 2 electrons that occupy the 1s2 subshell, and the extra electron then has n equal to 2 and an L of 0, and that configuration contains this extra electron. We can increase the atomic number and go so on and so on. The final topic in this chapter will be atomic radiation. So it turns out that X-rays are emitted when highly energetic electrons strike a metal target. This is actually how we produce X-rays for medical applications. If the electrons have enough energy, they can knock out a K shell, which corresponds to n equals 1 electron in a multi-electron atom. On the left, we have a diagram of the relative intensity of the radiation and the wavelength, and we can see 2 spikes, which we refer to as K alpha and K beta. As mentioned before, X-rays are used for medical imaging, amongst other applications. They are used to look for broken bones, since X-rays will pass through soft flesh, but they will not pass through bones. So one can shine X-rays onto a hand, for instance, and by seeing where the X-rays that survive the passage of the hand land exactly, one can see if the bone structure is normal or if it's indeed broken. We produce them by having a circuit with a voltage that has a heated filament. This emits electrons, and electrons are emitted in a very, very high electric field region. The electrons then smash into a piece of metal, and the X-rays are emitted towards the right. Now, the K alpha and K beta X-rays can be explained as follows. What happens is the high energy electrons hit an atom and they knock an electron out of the n equals 1 orbit. What then happens is an electron from the n equals 2 or the n equals 3 will travel down to the n equals 1 orbit. The electron will lose energy and emit an X-ray in the process. The more likely transition is from n equals 2 to n equals 1, which is the K alpha ray, compared to the n equals 3 to the n equals 1, which is the K beta ray, and that explains why K alpha X-rays are produced more when we look at the graph 2 slides before this slide. Lasers are another example of atomic radiation. The word laser is short for light amplification by stimulated emission of radiation. Spontaneous emission occurs when an electron in an excited state drops to a lower energy state. The loss of energy gets converted to a photon, which is produced in this process, and the photon will essentially be emitted in a random direction. Stimulated emission occurs when the atom is bombarded with photons of the emission wavelength, and this stimulates the transition to occur. We have an example here where we have an incident photon, and it stimulates the electron to drop from a higher energy to a lower energy, and the electron will emit a photon of the same wavelength as a result. The stimulated emission is in the same direction as the incident photon, and it also turns out that these photons will also have the same phase. Once one incoming photon produces two outgoing photons, this is how we essentially amplify the light intensity. Fluorescence occurs when electrons emit photons of various frequency when returning to the ground state. The example we have here is an electron that's been excited from the lowest state, and it goes to the energy level 3 state. It then drops to the second lowest state and finally drops to the lowest state, but there is a time lag in this process as its energy is being reduced. One example of a fluorescent compound is the green fluorescent protein GFP, and this essentially makes things glow in the dark. How this works is this absorbs photons which excite electrons, and then the electrons slowly decay to lower energy states, but as they do so, they lose energy and they emit photons in the form of light as they do so. The absorbed light will have a shorter wavelength because it corresponds to higher energies, and the emitted light will have a longer wavelength as it corresponds to lower energies, since the emitted light comes from smaller transition with respect to energy differences compared to what's absorbed.